Exact first order differential equations. Just as an example, they look something like this. X squared dy by dx plus 2xy equals e to the x. First order because they don't contain any derivatives beyond a first derivative. It's actually called a linear differential equation because it doesn't contain any fancy functions of y. By that I mean sine y, y squares, etc, etc. Okay, so how can we solve this? Well, a little bit of thought will show that the left-hand side could be rewritten using the product rule. And we'd get this. Have a quick check that you agree that d by dx of x squared y gives you x squared dy by dx plus 2xy. From here on in, we simply need to integrate each side with respect to x. The left-hand side, of course, is the integral of a derivative with respect to x, so we end up with just the function itself. You'll notice I did that in purple. I often skip that stage out and just follow the black arrow. We can integrate very easily with respect to x to give us the solution. And if we want to, or if we're asked to, we could make y the subject of the formula. That's very straightforward indeed. Make sure you understand that before continuing with the next part. The next part is what happens when the differential equation is not exact. So for example, dy by dx plus y tan x equals x cos x. At the moment, the left-hand side cannot be rewritten using the product rule. Now, not all differential equations of this type are going to be solvable anyway, but if we can solve them, the following technique is really rather neat. So just noting that that cannot be rewritten as the product rule d by dx of something yet. So what we try and do is we try and find a function which is called the integrating factor, such that we can multiply the given equation throughout by the integrating factor, and the left-hand side will become exact. Let's look at a general case. Imagine we were presented with this differential equation here. It's a first order linear differential equation. The first thing you've got to do is write it in standard form, and what that actually means is that it starts with just dy by dx. We can do that by dividing throughout by hx, and the following steps will show you what that looks like. It looks a bit messy, but then we can rewrite it one last time as shown, where wx over h of x is simply another function of x. We'll call it p of x. K of x over h of x is another function of x. We'll call it q of x. And in fact, we'll now write it down like this, where we understand that the capital P doesn't mean a constant, it means a function of x, and likewise q is another function of x. And what we're going to do now is suppose that a function I of x, we'll call it just I in a minute, exists, such that when we multiply throughout by it, the differential equation becomes exact. In other words, the left-hand side could be rewritten using the product rule. Okay, well let's multiply throughout by this integrating factor. We don't know its nature yet, but hopefully that'll come out during the process. And it would end up like this. Now, what we've assumed is that the integrating factor makes the left-hand side exact. And just looking at the first part, the I times dy by dx, this can only work if d by dx, let me do that again, if d by dx of iy is what it collapses to. Why? Well, because that will satisfy the I dy by dx when we differentiate. Let me just show you that differentiation. So if we do differentiate I times y, we'll get I dy by dx, which we can see we needed, and it also gives us this I dash y as well. So think very carefully at this point. What we're saying is, from the top line, the I dy by dx plus IPY is exact, and if that is the case, then we must be able to condense that down to d by dx of IY, and if we just differentiate d by dx of IY, then it gives us I dy by dx as we desired, and this other I dash y. Now we should be able to draw a very obvious conclusion here, and that is that I dash must be the same as IP in order for this all to be true. So we make that observation. Now what we actually need to know is what the nature of the integrating factor I is. So how do we find I from this? Well, if we rearrange it, we can write it as I dash over I equals P, and that happens to be one of my favourite little integrals. So if we integrate each side with respect to x, we end up with I dash over I dx equals integral of p dx. We can integrate the left hand side to give us the ln of I, so we've now got the ln of I equals the integral of p dx, and if we rewrite this using an exponential form, we've got that the integrating factor I, I've taken the positive aspect there, is equal to e to the integral of p dx, and that's called the integrating factor. So let's just summarise. The integrating factor is given by e to the integral of px dx, where the p of x comes from this standard differential equation as shown. That's pretty much all I use when I'm solving problems. One thing to note, when you're finding the integrating factor in practice, p of x of course will be a function, you do the integration. There's no need to put a constant on that particular integral, because if you do, all that happens when you multiply throughout by the integrating factor, it would just multiply throughout by a constant amount. You can try it if you want. I did it in class today, and you'll see just what happens there. So what would you do in practice? Well, okay, you'd find the integrating factor. You've got this. You multiply everything throughout by ix as shown to give you this line here. Now, you don't really need to do anything with the left-hand side, because the whole point of the integrating factor is that the left-hand side is now exact, which means that directly, with no thought, you can write down this line here. Once you've written it down, if you really want to, you could just make sure by differentiating out ix times by y that you get the line above. With real functions in, you will every time. And then finally, we can write down that I of x times y is equal to the integral of ix qx dx. The part in green, I use it in practice, but I actually just use the top two parts and work the problems through. Can it go wrong? Yeah, of course it can. If it happens that you can't integrate p of x dx, and this isn't going to work, at least not using this method it won't. And likewise at the bottom line, if you can't integrate I of x times q of x, then you're also going to have problems. But that's it, exact differential equations and integrating factors.